Hello, dear students. I am Samir Velankar. I welcome all of you to this next video on graph data structure. Well, in this video also, we are going to continue with DFS Traversal. We have come a long way in this topic. In the first video in this series, I explained how to manually check what is the output of DFS Traversal. In next video, I explained what is algorithm for DFS, which was recursive algorithm. Now, in this video, I will tell you what are the types of edges in DFS traversal of a graph. Now, basically, if you consider some graph may be directed or undirected, and when you perform a DFS traversal on that graph, you get a tree basically. So, what is the output? Output of DFS traversal. Now, output of DFS traversal on a graph, any type of graph for that matter, is always Now this fourth vertex has been explored or discovered at time 3. Now from 4, you can go only to one vertex, isn't it? There is only a directed edge to 6. So we will say discovery time of 6 is 4. Observe now, from 6, you can go only to 2. Check this. There is an edge from 6 to 2, but you can't go to 2. Why? Because 2 has been visited. You know DFS in and out. I'm sure you know. You won't go from 6 to 2 because 2 is already visited. So 6 is such a vertex which will not take us to any other new vertex. We call this type of vertices as dead end. That means 6 has been totally discovered and we should now shut down 6. That means this is the close time of 6 or end time of 6. Remember, the begin time of 6 was 4. So the end time, and after all, after 4, we don't have any vertex labeled as 5. So the end time of this sixth vertex is 5. And now you know what we do after we get a dead end. We will backtrack to the vertex from where we came to 6, isn't it? Well, we came to 6 from 4. So we are backtracking to 4. And now we ask 4, hello 4, do you have any adjacent vertex which is still pending? And 4 answers no, because you can see that 4 had only 6 as adjacent vertex. So now clearly fourth vertex is also a dead end. It won't take us to any new vertex. So this is the close time of 4 or end time. Now end time is 6 then. We are just ticking the clock by 1 every time. Now then, after 4 is a dead end, we will backtrack to 2, as you see, because we came to 4 from 2. If we are back to 2, 2 is also a dead end, you see, because 2 does not have any neighbors now, which can be explored. So end time of 2 has been discovered. End time is 7. I hope you know that end time means now we are never going to go to 2 again. Never. Because 2 has been totally explored and it has been closed at time equal to 7. So 2 is a dead end. So we will go back to 1. We are back at 1. But 1 cannot be closed because there are many neighbors of 1, rather 2 neighbors. The 2 neighbors of 1 still to be explored are 3 and 8. So you can go to any one of them. There is no such rule, as I said. Let's go to 3. But you would be correct if you go to 8 first. Okay, I am going to 3. So what's the start time, discover time of 3? Note that the last time the clock showed 7. So now the start time is 8. Let's go further. From 3, you can go only to 5. So the start time of 5 is 9. Now from 5, you have two options. You can go to 7. You can go to 7 or 8. You can select any one of them. I will select 7 in my DFS output. So 7 is where I'm going. So the start time of 7 or discovery time is 10. But it is clear that 7 is a dead end. So let's close 7. The end time of 7 will be 11. And we will backtrack. But if we backtrack to 5, if we come back to 5, 5 is still not a dead end, isn't it? From 5, you can go to 6. You can go to 6. So the discovery time of 6 is 12. Sorry, 8. I am so sorry. This was 8. You can go to 8 from 5. Discovery time is 8, and you can clearly see 8 does not have any edge which will take us to any new vertex now. So 8 is a dead end. So close time of 8 is 13. Okay, as this is a dead end, let's get back to 5. We came to 8 from 5, so we are coming back to 5. But when we come back to 5, 5 is also a dead end. Notice that 5 can still take us to 4, but 4 was already discovered and it was closed also. So visited vertex cannot be visited again. So 5 is a dead end, and we will say 5 is now closed at 14. Last time the clock shown 13. And we will backtrack to 3. But 3 has to be closed. It's clearly a dead end. So 15 is the close time of 3. And we will finally get back to 1. And 1 is closed at 16. Just check that this discovery time and close time, I have introduced these notions only to explain the types of edges. But in general, when you trace DFS, we are not interested in open or discover time and end time. So we don't spend time in writing these slash notation and discover time and end time. Okay. So what is the tree, by the way? What is the DFS tree? Let's see. Let's see the DFS tree. Now the edges which I have marked with red, were actually taken by our DFS traversal, isn't it? You can see these edges which I am marking. These edges were actually taken by DFS traversal, isn't it? So these are included in the tree. So we will get 1. From 1 we went to 2. Okay, from 2 you recall we went to 4. From 4 we are going to 6. But remember 6 was a dead end. So we came back to 4, then came back to 2, then came back to 1. 1 took us to 3. This was a tree edge. This we took. Then 3 to 5 we went. 5 to 7, but 7 was a dead end. So we came back to 5 and we went to 8. Of course, the directions have to be shown. It was a directed graph. You can see that there is absolutely no cycle in this structure which I have shown. This is a tree. So we actually had a graph, isn't it? But what happens when we do DFS traversal of a graph? We get a DFS tree. Now these edges which are included in the tree, which were members of the graph, these edges were there in the graph, isn't it? And they are the part of the tree, are called tree edges. I hope the definition is very clear. The edges which were taken by DFS traversal, that is the edges which are included in the DFS tree, are called tree edges. Yes, everyone. Now let's see the second type of edge called forward edge. Now the edges which were not taken, check the mouse cursor. See, this edge 1 to 8 was never taken by DFS. It was not added in the DFS tree. So these edges are simply cut. Similarly, 6 to 2, you observe this edge, 6 to 2 was never taken, or 5 to 4 was never taken. So 3 edges out of all the edges were not at all taken by DFS in our tree. Then these edges which are not taken will be one of these: forward edge or backward edge or cross edge. Let's see the definition first of all. What do you mean by forward edge? It is an edge u comma v. So u and v are vertices. So there is an edge from u vertex to v vertex such that u appears before v in DFS output. Just check what is the DFS output for this in sequence. From 1 we went to 2, from 2 we went to 4, from 4 to 6, 6 we backtrack to 1, 1 took us to 3, 3 to 5, 5 to 7, 7 to 8. This was the DFS output, isn't it? So coming back to the definition of forward edge, it is an edge u comma v where u and v are vertices such that u appears before v in DFS output and there is a path from u to v. In other words, v is descendant of u but not the part of DFS tree. You check that there should be an edge which is not the part of DFS tree. Only then it will be qualified to be a forward edge. Let's see an example. Okay, let's see an example. You see this edge 1 to 8. Check this edge 1 to 8 where the mouse is hovering. 1 to 8 is not added in the DFS tree, isn't it? So I will write it here. This edge is 1 comma 8. 1 comma 8 is the edge, vertex 1 to vertex 8. So you can label this as u and this as v. U is 1 and v is 8, isn't it? And u comma v is not the part of the tree. Now then, is this a forward edge or backward edge or cross edge? Now if u comes before v in the DFS output, what is u? U is 1. And what is v? V is 8. Is 1 coming before 8 in the DFS output? Just check the DFS output. Yes, 1 is coming before 8 in the DFS output, isn't it? Yes, it is true. 1 comma 8 and 1 is coming before 8 in the DFS output. But that's not enough. It's not that now it will be called as forward edge, because you see the definition says that u appears before v in the DFS output. Yes, 1 appears before 8, but there should be a path from u to v. And there is a path, come on, 1 to 8, there is direct edge from u to v. So definitely this 1 to 8 does not appear in DFS tree, and u comes before v. 1 comes before 8 in the DFS output, and there is a path from u to v, forward path we say, from start vertex to end vertex, u to v. So this edge will be labeled as forward edge. Let's see one more example. See this edge, 6 comma 2 is, check this edge, 6 comma 2. Now if you see this 6 comma 2 is the edge, 6 comma 2, then u is 6, u is 6 and v is 2. Now definition of forward edge is, if edge is u comma v, then u should appear before v in the DFS output. Let's see whether 6 appears before 2. U must appear before v. Whether 6 appears before 2? No, 6 appears after 2. In fact, 2 appears before 6, isn't it? So you see the definition of back edge. Back edge is, there is an edge u comma v, which is of course not the part of the tree. So there is an edge u comma v such that v appears before u in the DFS output. Now here v is 2. Observe the mouse. V is 2. 2 appears before 6. V appears before u in the DFS output. But that's not enough. That's not enough. See, v appears before u in the DFS output and there is a path from v to u. Now, is there any path from 2 to 6? Is there any path? Can you go from 2 to 6? Yes. From 2 to 6, you can go as follows: 2 to 4, 2 to 6. So, u comma v 6 comma 2 is a back edge. This is a back edge. Why? Come again. U comma v 6 comma 2 is a back edge because v comes before u in the DFS output. 2 comes before 6 in the DFS output, and there is a path from 2 to 6. That is, there is a path from v to u. V to u, 2 to 6. The path was 2 to 4, 4 to 6. All right. Let's see this edge now. 4 to 5. I'm writing it. Sorry, 5 to 4. I'm so sorry. 5 to 4. Okay. This was 1, then 2, then 3, then 4 start times, end time 5, then 6, then 7, isn't it? Then no start end time here, then 8, 9, 10, but 11 was the end time, then 12, and then 13, 13, then 14 was the end time here, then 15, and finally 16. Okay. Now let's consider an edge 5 comma 4. Now u is 5 and v is 4. Check this. If u is 5, here we are hovering the mouse, u comma v is the edge, 5 comma 4. Then let's see whether u comes before v, whether 5 comes before 4. No, 5 doesn't come before 4. In fact, 4 comes before 5. So you see that v comes before u. V comes before u. So it can be a back edge, but wait. Because v comes before u in the DFS output, it can be back edge, but there is one more criteria. There should be path from v to u. There should be path from v to u. Is there any path from 4 to 5? Let's see. From 4, you can go to 6 and then come back to 2, then 4. But you can't go from 4 to 5 at all. You just search this graph. There is no path from 4 to 5. So the second criteria for a back edge doesn't satisfy. This type of edge is cross edge. You can see a cross edge is the one where the edge exists in the graph and it is not added in the tree, and there is absolutely no other path from v to u. There is no path from v to u in that case, or rather uh, there is no way to go from v to u. If v appears before u, then such an edge is called cross edge. Cross edge. Some more things I have written in the definition. That is, in forward edge, we say V is descendant. These are very important from gate point of view. V is descendant of U. And in back edge, V is ancestor of U. And in cross edge, they don't have either ancestor or descendant relationship between them. Let's see, before we come to any conclusion, let's try to do DFS traversal on this graph. Of course, you can do DFS traversal in seconds now, but I'll be putting some time here. Let's start DFS from A. So A is discovered at 1. From A, you can either go to B, observe, you can go to B or C or D or F. You can go anywhere. There is no such rule, I repeat. But I'll be going to B. So B is discovered at time 2. From B, there is only one way you can go to D. Okay. D is discovered at 3. From D, you can go to F. Actually, you can go to E also or F. I will go to F. That's at 4. Now, you can see from F, you can't go anywhere. There is no adjacent vertex of F. Clearly observe the graph. So we have to close it down. The close time of F is 5. So we have to backtrack to D. But when we backtrack to D, D is still not dead because from D, you can go to E. So E is discovered at time 6. But clearly, E is a dead end because from E, you can observe from E, although you can go to F, but F is already closed. It was discovered. And E can take you to A, but A was also visited at discovery time 1. So it's time to close E also. E gets closed at 7. And then we will backtrack to D. We came to E from D. Now, when you are back at D, you can see that there is nothing to be explored on D. All adjacent vertices of D have been explored. So the close time of D is 8. And we will be back at B. We will be back at B. And B is clearly a dead end again. You observe that you can't go. You absolutely can't go to B. So B will be closed. I mean, from B, you can't go to any new vertex. So B will be closed at 9. Let's backtrack to 1. 1 is not dead because from 1 you can go to so many vertices, isn't it? Let's go to C. So the open time, the discovery time is 10 here. From C, we will not go to D because D was already discovered. We will go to E. But oh, I'm so sorry. E was also discovered. E was also visited, isn't it? E and F, D were visited. So C is a dead end. Clearly C is a dead end, isn't it? Now if C is a dead end, we will close it. So 11 is the close time of C. Let's backtrack. We'll backtrack to A. And now A is itself is a dead end because you can't go to F. F is discovered. You can't go to D. D is discovered. So 11 is closed to 12. What you observe in this example, very interestingly, is G and F were never discovered. That's because there was no way from start vertex A, there was no way to reach G, neither H. These are not reachable at all from the start vertex A. So these edges, which I am marking, are not at all added in the tree. These are not added in the tree. See, this edge is also not added in the tree. And they are not categorized as any type of edge. But just see which edges were not added. Let's consider A to D. Observe this. A to D was not at all added, isn't it? A to D is not added. So we can say U is A and V is D. Now, does U appear before V in the output? Yes, A appears before D because you see discovery time of A was 1 and discovery time of D was 3. So A was printed before D. So A comes before V, of course, before D. And is there any path from U to V? Yes, there is, of course, direct path from V. Sure, there is an edge from U to V. So this is a forward edge. I hope you are understanding. Let's take one more edge. Let's take A to F. Now, what is the relation of A to F? Let's see. You might have found out this is also forward edge. Now, U is A and V is F. Is U printed before V? Yes, U is printed before V. Discovery time of U, that is A, is 1 and discovery time of F is 4. And is there any path from U to V, A to F? Yes, there is a path. Direct edge is there. So this is also a forward edge or forward edge. Yeah. Let's consider E to F. E to F. So U is E and V is F. Is U printed before V? Let's see. Is U printed before V? Is E printed before F? No. Discovery time of E is 6. Discovery time of F is 4. In fact, F is printed before E. That is, V is printed before U here. I'll better write it. V, that is that is F, is printed or discovered before U, and U is E. So it can be a back edge now. It cannot be a forward edge, or it can be cross edge, isn't it? I hope you are understanding back edge, because V is discovered before U. So it can be back edge, but to be a back edge, one more criteria it should satisfy, that there should be a path from F to E. From V to U, there should be a path. Is there any path from F to E? Let's see. If you see the graph carefully, from F, you can't go anywhere. Hello, from F, there is no path at all. You can't go outwards. Forget about reaching E. There is absolutely no path from F to E. Then this type of edge is known as cross edge. Neither is ancestor or descendant of each other. Are you understanding? E or F, neither of them are ancestors or descendants of each other. Let's continue. Let's continue with one more edge. You can see that C to D was also not added, isn't it? Was not considered. So what is C to D? Which type of edge is it? Now U is C and V is D. Is C printed before D? Is U printed before V? Check, the discovery time of C is 10 and discovery time of D is 3. So in fact, D was printed before C. In fact, V was printed before U. V was printed before U. So it can be back edge. It can be, I'm not saying it will be back edge, but there is one more criteria. V is printed before U, and there should be path from V to U. Then only it is a back edge. So there should be a path from D to C. Let's see, is there any path from D to C? Absolutely not. You can see there is no path. You can go, of course, from D to F, but from F there is no path to C either. So there is no path from D to C. So this is also a cross edge. Any other edge which was not taken? Let's see. Oh yes, A to D we considered that. Oh, E to F, E to A. Let's take E to A. Observe the graph, E to A. So U and V are E and A respectively. Let's see whether E is printed before A or A is printed before E. Of course, A is printed before E. See their discovery times. That means V is printed before U. V is printed before U. So it can be back edge. But there is a criteria. V is printed before U, and there should be a path from V to U. Is there any path from V to U? Remember, V is A here. Yes, there is a path from V to U. A to C, C to E. So E to A is a back edge. I hope you have understood the definitions very well. You keep checking these definitions and reading them, and try to understand the meaning of them with these examples. Thank you very much.